Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and you are watching the Masterstroke series, where in this lecture I am going to discuss about alternating current, all the concepts. First of all, I am going to give you all the important concepts from this chapter if you want to review it quickly, and then I am going to discuss all the chapter concepts in one shot. So if you watch this video, everything, all the conceptual requirement for your KCET will be completed, and then we will solve some questions in our live session tomorrow. That is Monday morning 11 a.m. I am coming live with solution with the questions for 3 chapters. Okay, electromagnetic induction, alternating current, and I think moving charges and magnetism. These 3 chapters I will be covering in tomorrow's lecture. Okay. So let's start with the list of important concepts in this session. First we have DC and AC. So very important, very basic, but still you cannot skip it, the difference between AC and DC. Then we have AC applied to resistors and the corresponding concept of phasors from that. Then we have AC applied to inductors and capacitors. Then we have RL and RC circuits. We have series LCR circuit, and lastly we have transformers. So these are the 6 important concepts from this chapter, and in KCET exam you can expect up to 4 questions from this chapter. So this is a very important chapter, you cannot skip it at any cost. So let's start with the first concept, that is DC and AC. So DC, or direct current, is basically current that does not change its direction with time. So if you plot the value of voltage or current, okay, DC current, basically we are saying DC current, but when we say DC, we generally represent voltage. If you plot voltage against time, it does not change its direction with time. This is the ideal DC. So ideal DC is the value is constant, the direction is constant. Okay, this is an example of DC current. Okay, it is never becoming negative, it is always positive. Now AC, or alternating current, current that changes its direction with the time. So the direction is changed. So AC current, if you plot AC, okay, you will see that AC basically with time it is generally like this. Okay, changing its direction. So for some time it is positive along the positive y-axis, and for some time it is negative. It can be, the shape does not matter, shape can be any different types of shapes, but it is changing with time. That means it is an AC current, alternating current. Okay, AC varies as sine function, so we generally use sine function to represent AC. Later on you will see that different other functions are also applicable, but for this chapter, for this particular class, we will restrict ourselves into sine function only. So basically you can say that V is equal to Vm sin omega t. Now remember that sine function does not mean cos is excluded, cos is also part of sine function. Okay, so that is also part of it. So this is the, now let us look into the AC voltage applied to a resistor. So if you apply AC to a resistor, what will happen? We have seen that in DC, V is equal to IR, Ohm's law. Now what will happen to the Ohm's law in case of AC? So AC voltage is represented by Vm sin omega t. In case of DC, it was only V current, we could calculate the current. Now here also we have a current I. We are trying to find this current I when we apply this voltage Vm. So from there we can say that the same Ohm's law will be valid for your AC voltage as well. But obviously it will not be constant as like it was constant in case of DC current. Current will fluctuate, and you can calculate the current to be Vm sin omega t by R, and you can see that I equals to Im sin omega t. Here Im is basically Vm minus R. So what is the meaning of Vm? Vm is the maximum possible value of the input voltage. This is the maximum possible value of the input voltage. So this is the peak value. So if you go back to our previous example where I drawn the AC voltage, so AC voltage, so this is the maximum value, this is called amplitude, right? If you remember in the chapter waves, so this is basically Vm. in voltage. If you draw the same graph for current, you can call that maximum value of the current to be Im, and in this case this is the maximum value of the current Im. Okay, later on we will see another expression, that is RMS current and RMS voltage. We will see that and we will use that in future as well. So right now we are restricted to maximum current and maximum voltage as well. Similarly, we can do the same for RMS voltage and RMS current. Now power, what is the formula for power? Power, we know that power is equal to I square R. Okay, and you can apply that formula here as well. Now what is the average power consumed? So average power is basically given by, this is the symbol for average, that bracket, and I square Im square into R is basically a constant, right? So this is a constant that should come out of the average. So average means we are only taking the average of sine square in this case. Now average of sine theta or cos theta is 0. Okay, whereas average of sine square theta or cos square theta are half. So average of sine square theta is half, so we can say that average power consumed is half Im square into R. The average, how to calculate the average, that is a mathematical part. If you have learned this in mathematics, very well. If you have not learned it, no problem, you can just remember that average sine square average of sine square theta is basically half. Okay, as long as it is varying with time, the time variation should be there. So normally if you take just single constant theta, obviously average does not matter, it will have a fixed value, right? But if you are taking the time variance, because it is varying with time, that means sine theta can be 0 at some point, sine theta can be 1 at some point. So what will be the average? Sine theta can be -1 as well. In case of sine theta, average of sine theta, it is 0. In case of sine square theta, it is half. Okay, so from that logic, if we replace this half over here, we get that average power supplied in average power consumed in an AC is half Im square into R. So this is very, very important formula to remember. Now let's move on to the next part, that is to express AC power in the same form as DC power. P equals to I square R, as a special value of current is defined and used. It is called root mean square RMS or effective current, and it is denoted by capital I RMS or sometimes capital I. Now you have to remember that if in the previous case, if you followed me, okay, all the current and voltages were small letter. Okay, all the currents and voltages are small letter, but in the previous chapters, current electricity chapter, all the voltages and currents we generally used capital letters. Why so? So capital letter represents DC and small letter represents AC. Okay, now because RMS is kind of equivalent DC, that is why we denote RMS with capital letter. Okay, no other current can be represented by capital letter if you are talking about AC. You can denote RMS with small letter as well. So I RMS is fine. There is no problem writing like this. But if you are saying in case of AC, if you use capital I, that capital I definitely means it is RMS value only. Okay. Now, so I RMS is defined by Im by root 2. So I said that that there will be another value, that is I RMS. So I RMS is the root mean square. So generally average in case of AC does not matter. Average is basically what is the average of 1, 0 and -1? What is the average? Average is 1 plus 0 minus 1, so by 3, that is 0. So that means average is 0. But is this a good representation of these three numbers? This 0 is a good representation of these three numbers? Definitely not. Right? So if I say the RMS value, what they do? They just square all the numbers. They square all the numbers, then add them, and then they take a square root of that. So basically we have ignored all the negative values. Now what is we are left with? 1 square is 1, 0 square is 0, minus 1 square is another 1, so it is 3. So it is basically square root of 2 by 3. So this is not a 0 number, this is the RMS value. So average is 0, but RMS is not 0. So this is a good representation. Okay, this is very close to the average. So in case of this kind of variation of number, we generally use RMS values. Okay, so RMS is basically when you take the squares of individual numbers, then take a square root. Okay, so this is very, very important when you are dealing with sine function or cos function, because they vary a lot, right? So RMS is important, and RMS is basically represented by Im by root 2. Okay, and VRMS is again represented by Vm by root 2. So the power becomes, what is the power consumed? So power consumed, you can write average power consumed is basically V into VRMS into IRMS, or you can say it is IRMS square into R. How does it comes like that? So we have seen that in the previous case, power consumed is basically half Im into Im square R, right? That was the formula. So what is this? We can write this as Im divided by root 2 whole square into R. Now what is this? This is IRMS. So IRMS into R. So when you are writing like this, it must be IRMS. But if you are dividing by half, that means this is the peak value. So this is where students sometimes gets confused, especially while calculating powers. If RMS is given, you can simply treat it like DC. Simple. If average, if the maximum value is given, then you have to use the AC formulas. Otherwise, if RMS is given, 95% cases RMS will be given. So that cases you can treat it like DC. Okay, while calculating anything. But if you are dealing with AC values, maximum values, in that case you have to use your AC equations. Now let's see one numerical question. The frequency of an alternating current is 50 Hz. What is the minimum time taken by current to reach its peak value from RMS value? So what is the meaning of 50 Hz? So frequency is 50 Hz. So time period is basically 1 by 50. Right, this is the time period. Time period is 1 by 50 seconds. Now what is the meaning of time period? Time period means this is the one time period. This is the time taken by the wave to reach from here to here. This is one time period, right? Now how much time it is taken by the wave to reach from here to here? So the total time is capital T. The total time is capital T. That means this time must be equals to T by 4, right? This time must be T by 4, 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 right? So total time will be T. So the time period is 1 by 50 seconds. So T by 4, that is the minimum time required to attain from 0 to maximum. Okay, that is equals to 1 by 50 into 4. That is 1 by 200. Okay, 1 by 200 seconds. That can be written as 5 divided by 1000 seconds. So if you multiply 5 in both sides, so 5 into 10 to the power of minus 3 seconds is the answer. So 5 into 10 to the power of minus 3 second is the answer. So this is an easy question, but you need to know how to solve it. So first you have to find the time period from the frequency, then you can find this problem. Okay, next question, next part, we are talking about phasors. So in order to show the phase relationship between voltage and current in an AC circuit, we use the notion of phasors. So phasor basically represents whether current and voltage are in the same page, or someone is leading, someone is lagging. So how they are running after another. Okay, in case of DC we do not need phasor, because in case of DC current and voltages are always in phase. In DC current and voltage are always in phase, but AC current and voltage are not always in phase. That depends on the what circuit you are using. The analysis of an AC circuit is facilitated by the use of phasor diagram. A phasor is a vector which rotates about origin with the angular speed omega. So if you remember that if the frequency is f, then omega equals to 2 pi f. So if they give you the frequency of the sound of the AC wave, okay, you can convert it into omega by using this formula. So very careful. Based on that, objective question might come. What is phasor? Phasor is a scalar, phasor is a vector. Vector moving in a straight line, vector rotating around axis. So phasor is a vector rotating in an axis with the angular speed of omega, right? So this is how we represent phasor. Now in case of resistance, if you see, voltage was what? Voltage, input voltage. This is called input voltage, Vm sin omega t. What was the output current? Current generally considered to be output. So output current was Im sin omega t. So if you see, both of them are related with sin omega t only. So we can say that in case of resistance, they are in phase. If there is a difference between sin omega t, suppose this is sin omega t, this is cos omega t. So based on the sign of cos omega t plus or minus over here, we can say they are leading or lagging. And here you can see both of them are sin omega t, both of them are plus. So that means they are in phase. In phase diagram is drawn like this. So if you see that current and voltage are always together. Current and voltage, so this is voltage, this is current, they are always together, okay. So this is called in phase, and the phasor diagram is like this. So what is the meaning of this? So if you see that voltage and current always reaching to the maximum point together, going to the 0 point together, again going to the minimum point together, like this, okay. So this is, they are always synced. They are always synced with each other. So that is why it is called phase. And this is the phasor diagram. This rotates. So as the voltage is starting from 0, voltage started from 0 means the phasor is here. Now voltage goes to the maximum value. Voltage goes to the maximum value means this is the maximum value of the voltage. Now again voltage comes to the 0 value. Voltage comes to the 0 value means it comes here. Okay, and then voltage goes to the negative value. So this is the negative value. This is how it is rotating. Okay, so phasor is basically a rotating vector representing each and every point of this diagram. Now why we use this, not this? Because this will continue, right? This will continue and we have to draw a lot of troughs and peaks, right? So this diagram will take a lot of time to explain, but here after each rotation we can say how many rotations, how many waves have passed, that many times we will rotate it and we will find the location. Okay, that is why this is much more handier when we are dealing with AC, but this is a normal wave pattern, right? So this is why phasors are used in case of AC. Now next part is AC voltage applied to an inductor. Now again we are applying the same AC voltage Vm sin omega t to an inductor of inductance L. Then what will be the expression for current? The current through the inductor will be given by I equals to minus Vm by omega L cos omega t. There is a derivation for that. Derivation is not required. Formula is important. So derivation, if you want to check the derivation, I have done it in my 60 by 60 series, and again it is there in your textbook as well, but derivation is not required for your KCET preparation. So I equals to Vm by omega L cos omega t. So this is the formula for current through an inductor. So if you see, remember in the case of resistance, what was the current? In case of resistance, the current was I equals to Im by R sin omega t, right? So even though this term is different, there is a negative sign here, but this term you can say they are almost same, right? Sorry, I made a mistake. Just a simplification, it will be Vm. Okay, Vm. So there is a similarity between this and this. So we can say that this is basically the maximum value of the current. Okay, so we can replace it I equals to Vm by XL. Now what is this XL? XL has a similarity with the resistance. If you see here, omega L was in division, here R is in the division. So R plays the equivalent, this term XL plays the equivalent role as a resistance, right? XL is basically playing the role of resistance when inductor is connected to a circuit. And here XL equals to omega L is called the inductive reactance. Now as I said that omega is basically 2 pi f, so most of the cases the f will be given, frequency will be given. So whenever you want to calculate the inductive reactance XL, you have to use XL equals to 2 pi f into L. Okay, now let me go back to that initial equation again, and if you replace this with Im as I mentioned, then you will get that I equals to Im sine omega t minus pi by 2. So this, what was our starting point? Our starting point was Vm sine omega t. Now if you see the final expression, it is sine omega t minus pi by 2. So what we can say that here the current is basically lagging by an angle pi by 2. So current is lagging by an angle pi by 2. So in case of inductors, current lags the voltage by pi by 2. That means current is behind. So if the voltage is here, when voltage is here, the current is here. So when voltage is maximum, current is at 0. Similarly, when current is 0, voltage is minus 1. That means it is lagging behind. Okay, so whenever voltage is going to the maximum point, current is 0. Now when current is going to the maximum, voltage is 0. Current is going to the minimum value, voltage is 0. So that is how you can check. If when one is going to the maximum, another one is negative, when one is 0, another one is negative, then we say it is lagging in phase. Very careful. Okay, pi by 2 is easy to understand, but if the volt angle is anything other than pi by 2, then sometimes student gets confused. So you have to put 1, that is voltage. Voltage is important. Voltage is always fixed. So you have to put voltage ka value 0, starting point 0, first 0, and you have to see whether the current is positive or negative. If the current is in the negative side, that is here, that means it is lagging behind. Okay, it is lagging behind, right? If voltage is 0, that is voltage is 0 and increasing, current is negative, then we say it is lagging behind. So in this case, it is lags behind by an angle pi by 2, right? Now let's move on to the AC voltage applied to an inductor. So same thing, we now calculate the power. So how to calculate the power? Power, same formula, current into voltage, and you will get that current into voltage is basically Vm cos omega t sin omega t. Just simplify it, and then you can calculate the average value. The average value is again Im Vm by 2 sin 2 omega t. In case of resistance, it was sin square omega t. In case of inductor, it is sin 2 omega t. So sin 2 omega t, as I mentioned, that if it is sin theta, any version of sin theta, sin 2 theta, sin 5 theta, does not matter if theta varies with time, and if you try to find the average of that, that will be 0. So sin 2 omega t, average of sin 2 omega t is 0. That is why the average power consumed in an inductor in an AC circuit is 0. Okay, so very, very careful. Depending on that, lot of questions comes in your exam. Now next is AC applied to a capacitor. Again we are applying the same voltage, Vm sin omega t. So Vm sin omega t is common. We are applying the same voltage across all three components. Again you can find the current is basically given by Vm by 1 upon omega c. So the resistance, the role of resistance is played by here 1 upon omega c, and this is called 1 by xc. Okay, so 1 upon xc, xc is called capacitive reactance. Okay, so it is, the name is similar to that of resistance, but instead of calling it resistance, inductive reactance, capacitive reactance, and also remember that they have the same unit as resistance. Okay, their unit is ohm only. In previous case also the unit of inductive reactance also ohm. Okay, the unit is ohm for all three, resistance, capacitive reactance, inductive reactance, unit is ohm. And you can write this as 1 Im sin omega t plus pi by 2. This equation, obviously you can write it like this. Now you have to also remember that xc is basically given by 1 upon omega c, that is 1 upon root 1 upon 2 pi fc. Okay, 2 pi fc. This is the formula that you should remember. So in this case, the current is given by Im sin omega t plus pi by 2. So basically you can say that current is leading the voltage, right? So current leads the voltage by angle pi by 2. So phasor means here, as you can see, the current is ahead of voltage. So whenever the voltage is 0, the current is positive and it is the maximum position. That is why the angle between them is always 90 degrees. Okay, so in case of inductor, current lags the voltage by pi by 2. In case of capacitor, current leads the voltage by angle pi by 2. So this is clear. Now let's move on to the next part, where again we will calculate the power in the capacitor. So again you can see that the average power consumed in a capacitor is again 0, similar to that of the inductor. Okay, so pure inductor, pure capacitor does not consume any power. Okay, power consumption is 0. Now let's move on to another important concept, that is RL circuit. Okay, so RL circuit is basically inductor and resistances are connected in series. Okay, so they are connected in series. Parallel combination is possible, but that is not part of our syllabus, and not even until if you study in physics, and if you are doing BSc in physics, you will study parallel combination as well. Otherwise parallel is not required. Now in this case, the impedance is basically given by R equals to Z equals to R plus XL. So this is R, this is XL, inductive reactance, right? So XL, so they can be considered as a simple series connection, and you can say the inductance is basically R plus XL, or you can say R plus omega L, or R plus 2 pi FL. Okay, now you can calculate the current in this case as well, and current is basically Im sin omega t. So the phase in this case, obviously if you see that phase is not super clear, so Im is basically Im is basically Vm by Z, right? So this is not the phase is not super clear. You can calculate the phase in this case. We will see a common formula to calculate phase, and based on that you can calculate the phase for even RL or simple RC circuit as well. We will see that. Now RC circuit, again same thing. Here R and C are in series, and in this case the impedance, this is called impedance. Okay, impedance means basically equivalent resistance in case of AC circuit. Impedance is nothing but equivalent resistance in AC circuit, and you can calculate this by 1 by omega c, or 1 by 2 pi fc. Okay, 2 pi fc, and similar to that, current can be calculated using this simple formula. Okay, and now we will talk about LCR circuit, the most important. LCR connected in series. LCR connected in series. Okay, so first of all you can calculate the formula, that VL. First of all you have to realize that whatever is the voltage drop, okay, with the magnitude, okay, magnitude, the sign will be not the same. So VL, VC and VR, they are across these components, and that should be equals to whatever the voltage of the source that you applied. Okay, in terms of AC voltages, you can write is individual voltage drop across them can be written by V square equals to VR square plus VL square minus VC square. Very important. There is a mistake here. The mistake is, it is VL minus VC whole square. Okay, so VL minus VC whole square is the formula. Okay, so you have to remember this formula to calculate the average power. Okay, again there is a mistake here. It is IL into XL minus XC whole square. From here you can calculate the impedance of the circuit. Okay, you can calculate the impedance which will turn out to be XL minus XC whole square. Okay, so average impedance is given by XL minus XC whole square. So XL and XC basically generally we consider in this case XL is greater than XC. We have assumed in our head XL is greater than XC, which is most of the cases is true. Some cases if you see that XC is greater than XL, then what you have to do, you have to just reverse this XC minus XL whole square. Okay, if XL is greater than XC, the circuit is said to be inductive. If XC is greater than XL, then circuit is said to be capacitive. Based on that, different forms appear. We will see that in a while. Now, in a series LCR circuit, R is 300 ohm, L is 0.9 Henry and C is 0.2 microfarad and omega is 1000 radian per second. Then the impedance of the circuit is, you have to calculate the impedance of the circuit. How to do that? First stage is we will calculate XL. XL is omega L. So omega is 1000 and L is 0.9, that is 900 ohm. Okay, what is XC? Now we will calculate XC. XC is 1 by omega C. Okay, so 1 by omega is 1000 and C is 2 microfarad. Microfarad means 10 to the power of minus 6 in the division. Okay, so you can cancel this. You will get 1 by 2 into 10 to the power of minus 3, right? 1000 minus 6 minus 3. Now this minus 3 will go up and it will become positive. So XC is becoming 10 to the power 3 by 2, that is 1000 divided by 2, that is 500 ohm. Okay, so what is the impedance Z? Z is basically R square plus XL minus XC whole square, that is R is given by 300 ohm, 300 whole square plus XL is 900 minus XC is 500 whole square, so it will be 300 square plus 400 square, right? Now if you remember that there is a thing that 3 square plus 4 square square root is basically 5. Okay, you can check that out and tell me if you forgot. Now here is similarly we can write this as 500. Okay, 300 square 400 square will be 500 square whole root. So 500 ohm is the equivalent resistance or impedance of the circuit. So 500 is the answer. Easy question. Let's move on to the formula. Somehow that typing error continues here as well. So it will be IM, maximum current is basically given by Vm by XL minus XC whole square. So that is Vm by Z, basically Vm by Z. So you can say that this is basically Vm by Z. Okay, that is how you can calculate the maximum current. Okay, now if XL equals to XC, then this becomes 0. If XL becomes equals to XC, then you get 0. So IM becomes Vm minus R. This is the maximum current in the circuit. This condition is called resonance. Okay, very important, resonance in LCR circuit. This corresponds to the angular frequency omega naught. So omega naught is given by 1 by square root of LC. Corresponding frequency is given by 1 by 2 pi square root of LC. Okay, both are important. Based on that, questions will come. It has come and will come in your KCET exam as well. Not maybe maybe not year, but in future years, whenever you are appearing for KCET, you have to be aware of what is the formula for resonance and when it is happening. So resonance is happening when XL becomes equal to XC. Okay. So now if you see that phase difference is given by, I said I will give you the formula for phase difference. Phase difference is given by XL minus XC by R. Okay, this is the phase difference phi. Okay, in case of normal LR circuit, okay, LC circuit, LR circuit, the phase difference is XL by R. In case of normal CR circuit, it is XC by R. Okay, but there is a negative sign, but negative sign you can ignore for that angle. Okay, it will be XC by R in case of a normal CR circuit. Okay, so that is how you can either put XL equals to 0 or XC equals to 0 to calculate the corresponding phase. Now this is the graph, okay, this is the voltage, this is the current, okay, as they are varying. Okay, so this is the different this is both cases, this is current, maximum current, and how they are changing, okay, based on whatever you are applying. So for a particular given circuit, this is the maximum resonance. Okay, so current suddenly increases at resonance frequency. Now let's move on. The power in LCR circuit, power formula again is P equals to V into I. Okay, now in pure inductor, pure capacitor, it was 0. Will it be 0 for LCR circuit as well? So let's see. So power is basically, you can calculate it to be P equals to V RMS I RMS cos phi, right? So there is a term called cos phi. What is that phi? Phi is basically the same phase difference that you have calculated, that is phi equals to tan inverse XL minus XC divided by R. Okay, so that was the phase difference. So this is the called this term cos phi is called power factor. Okay, this can also be concluded using this value I square Z. Okay, same formula. If you know RMS value, if you know the impedance, you can calculate power using I square Z as well. Okay, now if you remember that the power this cos phi is called power factor. Now case number 1, resistive circuit. If the circuit contains only pure R, it is called resistive. In that case, phi equals to 0, that is cos phi equals to 1. There is the maximum power dissipation. So for pure resistive circuit, power factor is 1. Power factor equals to 1. Lot of question, lot of MCQs, different version of MCQs come from this. Okay, in your board exam as well, in your KCET exam as well. Purely inductive or capacitive circuit. If the circuit contains only an inductor or capacitor, we know that the phase difference between voltage and current is pi by 2. Therefore, cos phi is 0. So, no power is dissipated even though the current in the flowing circuit. This current is something referred to as wattless current. This is called wattless current. So, in future, if your parents call you wattless, then you should know that what is the meaning of wattless. So, current is passing, but the no work is basically done. So that is why it is called wattless current. This was a very popular slang in some previous generation. Okay, the generation before myself also. Okay, I have seen that in older Amrish Puri movies that wattless, you are a wattless. So wattless means that term actually refers to this. So current is flowing but no work is done, no power is consumed. Right now power. So the case number 3, series LCR circuit. So phi is basically given by tan inverse XL minus XC by R. So phi may be non-zero in an RL or RC or RCL circuit. Even in such cases, power is dissipated only in the resistor. So power is only dissipated in the resistor. Okay, power dissipated at resonance in LCR circuit, as in resonance XL minus XC becomes 0. So phi also becomes 0. So power dissipated again becomes maximum. So that is the maximum power is dissipated through R at resonance. Again, power factor is 1. Power factor is 1. Power factor 1 means maximum power dissipated. It is less than 1 means not exactly power is dissipated. This 0 means no power dissipated. Okay, now last topic of the day, that is transformer. So transformer basically have two coils. One is primary, another one is secondary. Now for many purposes it is necessary to change or transform an alternating voltage from one to another of greater or smaller value. So we can transform an AC voltage of higher value or lower value depending upon our requirement. Okay, this is done with a device called transformer using the principle of mutual induction. So transformer works on the principle of mutual induction. So as the current varies in this primary, okay, there is an induced current in the secondary. Okay, so primary the current is and it is only possible for AC, as you know, because AC automatically changes over time. time, right? For each cycle it is changing twice, positive to 0, 0 to positive, 0 to negative, like that. So it is changing, each cycle it is changing. So what we can say, that whatever the flask is changing, that flask is getting linked with the secondary. So secondary flux linkage means there is a induced current in the secondary as well. So that is how the primary and secondary are connected with one another. Now, so Vs by Vp, that is the secondary voltage, output voltage that we are interested in, is basically Vs by Vp. This is the input voltage, is Ns by Np, number of turns in the secondary divided by number of turns in primary. So V is basically proportional to number of turns. So if you want to step it up, you have to keep more number of turns in the secondary. We'll see that in a while. So Ip Vp is Is Vs. But in terms of power consumed in an ideal transformer, power consumed should be equal. Okay, so thus the power input is equal to the power output in an ideal transformer. Okay, now let's see what else. You can convert this into in terms of current as well. So Ip by Is equals to Ns by Np. Okay, also what else, that if number of turns in the secondary is more than number of turns in primary, it is called a step up transformer. If number of turns in the secondary is less than that of number of turns in primary, it is called a step down. Okay, step down transformer are used just before it is reaching to your home. Okay, step up transformer are used when it is coming from the power station towards your city. Okay, now a 100-watt bulb is connected to an AC source of 220 volt 50 Hz. Then the current flowing through the bulb is. Interesting question. The power rating is given 100-watt bulb. Okay, and it is given that AC source of 220 volt 50 Hz. Okay, then the current flowing through the bulb is. How can we calculate the current? Power is given, voltage is given. Okay, now this voltage is RMS voltage. Okay, so they have not given anything other than the current flowing through, so we will assume that they are talking us about the RMS current only. So we know that power is basically IRMS VRMS. Generally this value 220 volt 50 Hz, this 220 volt always represents VRMS. Power of the bulb is 100 watt. So 100 is equals to IRMS into V is 220 volt. So IRMS is basically equals to 100 divided by 220. Okay, so it will be 10 or 5 by 11. Okay, so 5 by 11 ampere is the current that is passing through this bulb. So correct answer is option A. So don't get confused. No inductor is given, no capacitor is given. How to solve it? Don't worry, just use the normal law. You can still find the answer. So this is a very easy question which student gets stumbled upon by seeing the question AC, but the power rating is given in DC. How to solve it? Don't worry, we know the formula. Apply it, you will find the answer, right? So we have reached the end of this lecture, and I will be back with the live session tomorrow morning 11 AM. Be ready for that. See you in the live session. Till then, bye.